Hi everyone. So today we are going to dive into the book that we chose earlier, Dynamics of Polymeric Liquids, the Holy Bible of the Rheology, I would call it. It's written by Bob Bird, Armstrong, and Ole Hasseger. Um, so the first part of the book is discussing the Newtonian and non-Newtonian behaviors and comparing them. In the first chapter, they start with a review of Newtonian fluid dynamics. So they talk about the equations of change in terms of flux, and the beautiful about thing about that is that you can use this for both Newtonian fluid and non-Newtonian fluids. So what I'm going to talk about during the next few episodes when we're talking about the equations of change, this would be valid for all of the liquids essentially. And So these equations are going to show how the mass, momentum, or energy of a fluid changes in time and space. We are going to start with the conservation of mass equation. So this is the sort of equation that we are generally looking at. So variation of density in time is going to balance a divergence of mass flux essentially. So rho is the density, u is the velocity vector, and we want to see if we can understand this equation a bit more. So if you look at the book, they start with talking about the mass flux which is coming through a surface. So they chose a control volume. So this is an arbitrary shape of control volume. So this has a volume of V, and the surface of S. So this control volume, you can choose a tiny element over there, and which has a ds surface. So you call it a surface element. And so to talk about the mass flux which is passing through across this tiny element ds, you need to know the normal vector which is directing outside of the control volume at this tiny element. So n is showing it's a unit normal vector. So it's unit. So the size of that is there is something wrong with my dictation today. It's not really good in any way. So so it's a unit normal vector. So the size of the normal vector is 1, and it's actually pointing out outwardly. So it's you can call it an outwardly directed. So it's outwardly directed unit normal vector n. So I want to know how much mass flux is coming through the surface ds inside my control volume. So that would be literally your mass flux, which is rho u, multiplied by ds. But the issue is that the velocity is not necessarily perpendicular to the surface. So you need to use a dot product of that with a normal vector n. That's why we defined n. So let's just recall that n dot u is giving you the component of u in n direction. All right, so this is the mass flow rate. So this is the mass flow rate which is coming through the control volume through this tiny little surface ds. And if I want to talk about the law of conservation of mass, it's telling me that variation of mass inside my control volume, so that if I want to write it mathematically, so it's variation of mass in time inside my control volume, which is density multiplied by dV. So density I integrated inside my control volume, and how it's changing in time. So this is giving me rate of increase of mass of fluid within my control volume V. So this is going to be equal to amount of the fluid which is coming across my cross sections. So for a tiny ds, I show you that this is going to be n rho u, the inner product of that by ds. So if I integrate it over my surface, this is the amount of the fluid which is coming inside my control volume. So this would be rate of addition of mass across the surface S. So this is the law of conservation of mass, right? So variation of increase of mass of my fluid inside my control volume. So inside my control volume here, that would be variation in time if I integrate over density on my control volume, is equal to the amount of the fluid which is coming across your cross section. You know, this ds tiny little one. If I integrate it over the whole surface, which is giving me this integration over s, this is going to be law of conservation of mass. So this is not really nice, right? So you have integration over control volume and also integration over surface of the control volume. To make it a bit more interesting, you can use Gauss's divergence theorem. Let's note that it's a theorem, so it's not proved. People just know that this is correct, but you cannot mathematically prove it. I'm going to give you an example to just give you a sense of what does it mean. So if you use Gauss's divergence theorem, you can replace this term, which is integration over surface, and you can replace it with a control volume integral, which is much more nicer. So if I rewrite these equations, so what I had was differentiation of the mass inside my control volume was equal to that term. I'm going to use a divergence theory, which is giving me divergence of mass flux in dV. So this is actually quite cute, right? So I replaced that term, which was integration over surface, with a term which is integration over control volume by using Gauss's divergence theorem, which there is no proof of that. And if you do that, you can bring everything inside one integral, right? So you have a big integral of control volume, which is showing you the variation of density in time, plus divergence of flux, which is rho u. If you integrate it inside your control volume, that would be equal to 0. This is an arbitrary control volume, so I can just say that variation of density in time plus divergence of flux is equal to 0. And this is the conservation of mass. So conservation of mass or continuity equation. So literally telling you that the amount of the if your density is changing in time, this would be equal to the divergence of the flux. So what happened here was like we chose a control volume. We figure out how much fluid is passing through a tiny element at the surface of that, which was n dot rho u ds. So I'm using the dot product because I want to get the component of u in n direction. And okay, so I know how much the fluid is coming through my control surface. So if I integrate it over the surface of my control volume, that would tell me how much the mass of my fluid is increased inside the control volume. This gets a bit weird, right? You have integration over surface, integration over control volume, and it's not really nice to use this if you're using CFD software, for instance. So what you do is you use the Gauss's divergence theorem. It's a theorem. There's no proof. People just know that this is correct. I'm going to give you an example to explain why this is correct using a Taylor series expansion. And you can replace this term, which was the integration over surface, with integration over control volume. So if you do that, you end up with this equation here. And now I can bring everything inside one control volume integral. So I have this term and this term appearing here. And integration of this term is equal to 0. It's an arbitrary control volume, so you can just say that the integrand is equal to 0. All right, so let's talk a little about this strange Gauss's divergence theorem. So it tells you if I integrate the amount of the fluid which is coming through surfaces inside my control volume, I can replace it with the divergence of flux. With the integration inside my control volume. So what does it mean exactly? This is quite an interesting thing. So you can use a Taylor series expansion to show that. Let me actually show you that. It's a really cute and simple things that one can do. So the first thing is I need a control volume. So okay, let's define things now. So you have a velocity vector which has ux and uy, and let's say the z component is 0, just to make our life easy. And I have a control volume which is like this. I use a cube control volume. So I have dx, dy, and then I have dz, right? So this is dz, this is dy, and this is dx. All right. So the amount of the fluid which is coming inside this is 3D, right? All right, so the amount of the fluid which is coming through the x direction, I'm going to use a red color. So the amount of the fluid which is coming through that surface is rho ux. So rho ux multiplied by dz dy. So dz dy is coming in. And okay, let me wipe this thing out. Don't create a mess. I have a tendency to create a mess quite easily. And the amount of the fluid which is coming in x direction from the other surface would be, if I use a Taylor series expansion, that would be rho ux plus variation of rho ux in x direction multiplied by dx multiplied by dy dz, right? So this is using Taylor series expansion. Okay, I can do the same in y direction. So I'm using the green color now. So the amount of the fluid which is coming from that surface from the bottom would be rho uy dx dz, and the amount of the fluid which is coming out from that surface on the top would be rho uy plus variation of rho uy in y direction dy multiplied by dx dz, which is, again, this one is also Taylor expansion. All right, so if I look at my law of conservation of mass, let me rewrite it here again before we take any step further. So that would the variation of density in my control volume was equal to minus of integration of n rho u ds over control surface. If I do that, I write things down. So I just showed you how much mass is coming through different surfaces. So these are these terms and these terms here. So this would be this side of equation. And the variation in time of the control volume would be, so okay, rho dx dy dz, right? And this is variation in time, which is equal to the amount of the mass that is coming from different surfaces. So in x direction, in left, I had this term. So that would be rho ux dz dy coming in. There is a minus sign here. Let's not forget about that one. So this is in x direction coming in, and what is going out would be, again, it already has a negative sign because it's coming in. So normal vector and the velocity are in opposite direction over there. And what is coming out would be rho ux plus rho ux variation of that in x direction dx dy dz, right? This was in x direction. If I plus the amount of the fluid which is coming from the in the y direction, right? So that would be okay. So rho uy dx dz, that has a negative sign, and the other one has rho uy plus rho uy dy dx dz. Right. So if I look at if I simplify the equation in the left, in red, the amount of the fluid which is coming in and coming out in the x direction, you can cancel this term with this term out, and so this would be that. And in y direction, you can cancel this term with this term out, and so the right side of the equation, this term, would be, so the left side would be variation of density in time, dx, dy, dz, would be equal to variation of rho ux dx, dx, dy, dz, plus variation of rho uy dy, again multiplied by dx, dy, dz. This is quite interesting, right? I started by integrating over a control surface, but I have dx, dy, dz appearing here, which is like integration over control volume that we have here, right? So I can literally cancel these things out, and I would end up with variation of density with time is equal to variation of flux in x direction plus there's a minus sign, let's not forget about that, flux in y direction. And okay, I got from there to this point, and if you recall gradient definition, that would be the x I plus dy j, and the divergence of velocity would be ux dx plus uy dy. So if I look at this and this, I literally can say that the variation of density in time is equal to minus divergence of velocity. So let's see what happens here. So I started with the conservation of mass, which was integration of, where was it? There it is. Yeah. So which was the integration of over the control volume, mass inside the control volume, and it was showing that if there's a change inside the mass of the control volume, it's actually due to amount of the fluid which is coming through the control surface. And I just said that, divergence theorem of Gauss tells you that you can replace it with divergence term if you integrate over control volume, but there's no proof of that. So I use the Taylor series example to show you that. So if I have a fluid which is coming in the x direction inside my control volume, which is this amount of the fluid, and the amount of the fluid which is coming out is in this amount. I use the Taylor series expansion to show you that. And if I do the same for in y direction, the amount of the fluid which is coming in is this one, the amount of the fluid which is coming out is this amount. And if I look at the law of conservation of mass, I had the control volume thing that, so that's literally variation of density in time, multiply dx, dy, dz, it's control volume. And that was equal to integration over control surface. So I need to add all of the mass flux inside from different at different control surfaces. So in x direction, I know that how much of the fluid is coming from the left side, which was this amount here, and then I have this amount of the fluid coming out in y direction. This amount was coming in. This was the amount of the fluid which is coming out. If I add them together, I would end up with this. So variation of density in time is equal to variation of flux in x direction plus variation of flux in y direction. And we know the definition of gradient. We can define the divergence, and we see that variation of density in time is indeed equal to variation of the divergence of flux, essentially. So we got to the Gauss's divergence theorem by integrating over surface, essentially. All right. So what I got was this equation here, which we call it conservation of mass, or some people call it continuity equation, and I use this time derivative, which is a regular time derivative, but I would rather rewrite this equation in this form, use a different time derivative, which we call it material time derivative, and that would be equal to density multiplied by divergence of velocity. If I define the material time derivative to be regular time derivative plus a convective term, which is this one. So this is actually a more appropriate way of writing this equation. You know, the one that I write on the top, this is using this time derivative, which is people in Lagrangian perspective are using it. In fluid dynamics, we have a tendency to use this time derivative. We call it material time derivative, or this appear more naturally in Eulerian perspective. We call it material time derivative, or I think in Baird's book they call it to substantial time derivative, if I'm not mistaken. I'm not going to go through the detail. I probably created another video later, and we'll go through the difference between this Lagrangian or Eulerian time derivatives. There are actually plenty of other time derivatives that we're going to dive into them in this book. So it would be nice to clarify between the difference in these two in the first steps, and later address the other ones. So hopefully see you soon with another video about the difference between a time derivative, a regular time derivative, and a material or substantial time derivative. Have a good time, everyone. Bye.